So we're back. That was kind of fun. As soon as the video stopped, just like on cue, the lights went out, and so I was able to remember that the video stopped. But I started talking about if we had a garage door transformer or a doorbell transformer, that's going to be something that you, as electricians, power up. You're going to buy the little transformer, and you're going to hook it up somewhere, and you're going to put 120 volts on it, right? So let's take a look at that circuit really quickly. I got 120 volts, some source, and that's probably on a 15 amp circuit, right? 15 amp OCPD, let's say, on the hot side. And then you're essentially going to wire nut it to the internal primary of your little box transformer that you're going to hang on the side of a box. Again, for a doorbell, an alarm system, a garage door opener, puck lights, whatever. Things like that take a little transformer. And then inside of that transformer is going to be a secondary coil. And that's probably going to be a step down, and then it's going to run whatever load it does. You know, the garage door opener signal, probably just for the garage door opener, because it's got its own 120 volt AC motor. Doorbell is going to ring and chime. Puck lights, it's going to turn on the puck lights, and that actually will be powered from this guy. So this guy usually is going to be something like it's going to be rated for 16 to 24 volts. And it'll be AC. A lot of people think that's a DC transformer. Now, some of your puck lights and some of your other things, this will not just be a secondary, but it'll also have a rectifier, which is a circuit that if you watched early in the chapters of the book, it's a circuit that turns AC into DC. It runs it through a bridge rectifier, so it's always going the same direction, and then it runs it through a filter, so it turns this circuit into this circuit first, right? And then it actually clips this circuit with its filter, and it turns it into what you end up looking like is just this nice AC voltage, which I don't know if those lines mean anything to you or not. But the one we're going to work on is simply an AC transformer. And it's a step down. If I've got 120 volts and I need to get to somewhere around 24 volts, I probably need to step this guy down about 5 times or more, don't I? Like 5 or 6 times. Let's go ahead and try as a 6 to 1 step down. Just see what happens. 6 to 1. I said 5 because I know 24 is a fifth of 120. And I only know that because 12 is a tenth of 120, and I doubled it, right? So that's the way I do math in my head. So let's call it a 6 to 1 and just see what happens if it's a 6 to 1 transformer. The first thing is I've got 120 volts, so 120 volts divided by 6, which is essentially what I'm doing. I'm taking a sixth of the 120, and what does that add up to? Well, that adds up to 20 volts. 20 volts. So I have stepped that guy down to 20 volts, which is, you know, halfway between 16 and 24. So that's pretty good, because you know that the actual voltage in our 120 volt circuit is going to fluctuate. You guys know that as electricians. You stick your voltmeter in there. This guy can operate anywhere between 16 and 24. Take a look at the little charger on your iPad or your iPhones or your Androids or whatever. The little wall wart that you plug in and then you plug the cord into that. That's going to have a voltage rating on it. It's probably going to have a current rating too. That's simply just a transformer. Now it's also got a rectifier, and it turns that AC into DC, I believe. But it's definitely a transformer among other things in there. And you'll notice that that transformer actually is a transformer that can take all sorts of different voltages. I think the last time I looked at an iPod transformer, iPhone transformer, wall wart, it said it could run anywhere between 90 and 300 volts. So the nice thing about that is you can plug it in anywhere in the world and it's probably going to work for you. And it takes that voltage and it's got some electronics that change the ratio in the internal transformer. It also has some electronic circuitry that can clip the signal that's coming out of that thing to turn it into the correct DC voltage that it needs. Which I don't even know what that voltage is. 5? I know it's like 5 in computers. I have no idea what it is on an iPhone. But that's what's going on in that wall wart transformer. Now, this particular transformer in the wall warts, you guys, those of you who hooked them up, you know that you have the hot, and you have, in fact, it would be over here, wouldn't it? You have a hot, and you have a neutral, because this is the box that the transformer lives in, right? It's to here, and you're just wiring it up with wire nuts here and here. It's got a hot and it's got a neutral. It's probably also got a ground wire that's hooked up to something. Wow, I don't know if you guys can hear it, but it's Monday morning and I'm at the JTC and it is raining hard outside. June 8th, I guess, or 9th. I think it's the 8th today. I think it's the 9th. Anyways, we ground that thing. Internal to this, there is an actual connection between the neutral of that and the neutral of this. And that is because we can't have this part of it ungrounded. Remember I was telling you earlier, isolation transformer, there's no electrical connection between. The code requires on any downstream small transformers that they be grounded. The ballasts in your fluorescent lights are all essentially transformers. They are all what they call auto transformers. It's not that they do anything automatically, it's that they have an electrical connection between one side of the coil. And all that does is stabilize these two things to that same neutral voltage, which should be the same as the potential to ground. And that's just a safety item. It also means that that transformer will theoretically conduct any noise or signal on it. So sometimes people want isolation transformers and ground them in a different way to get rid of some of the signal coming in. Transformers are essentially all the same thing. They're just two sets of coils connected together in such a way as the voltage from the one induces a voltage on the other in some other flavor of voltage, upper or higher or lower, up or down. Again, on this one, whatever current is drawn here is going to actually only reflect 1/6 of the current here. So if this guy, when you ring the doorbell, let's say it draws 2 amps when you ring that doorbell. Over here, it's only going to draw 2/6 of an amp, or 1/3 of an amp. 2 amps divided by the turns ratio backward. Less current here, more voltage here. More voltage here, less current. The less current times more voltage is always going to equal the more voltage times less current, because power is going to be the same. Power in this is the power in the same as in this. Power in equals power out. That's it for that. I think I'm going to do one more quick video starting on 3-phase.